All right, we're now going to look at the second group of examples down here. So in healthy adults, caffeine has an average half-life of 6 hours. That means the amount of caffeine decreases by 50% every 6 hours. A person drinks a cup of coffee containing 100 milligrams of caffeine at noon. Each of the following expressions describes the amount of caffeine in the body predicted by an exponential model at some point in time after consumption. How many hours after consumption? So we have our initial value of 100. Our decay factor is a half because our amount of caffeine is decaying or decreasing by 50%. So the question is, how much time do these exponents represent? So the key is that it decreases by 50%. It decreases by 50% every 6 hours, which means that each exponent represents a 6-hour period. So if the exponent is 1, as it is in part A, that does not mean that it's telling me the caffeine an hour later. It's telling me the caffeine how many 6-hour periods later. So this actually represents the amount of caffeine left in the body after 6 hours, because 6 hours is the same as one 6-hour time period. 1 6-hour time period. Okay. Whereas, for example, in part B, okay, our exponent this time is 3. So that's not going to tell me the caffeine after 3 hours. It's going to tell me the caffeine after 3 6-hour time periods. So 18 hours total. 3 6-hour time periods. If I were to calculate that, that would tell me the amount of caffeine left in the body after 18 hours. Okay. Now in part C, now we're mixing things up. Now we have an exponent of a half. Okay, so an exponent of a half means a half of a 6-hour time period. Well, half of a 6-hour time period is actually 3 hours. So it's a half of a 6-hour time period, which is 3 hours. Okay. And then lastly, part D, now we have an exponent of 5/6. Okay. So this is going to tell me the amount of caffeine left in the body after 5/6 of a 6-hour time period. So 5/6 of a 6-hour time period is going to is going to be 5 hours. 5/6 of a 6-hour time period. Okay, so part D will tell me the amount of caffeine left in the body after 5 hours. Number 7, write an expression to represent the amount of caffeine left in the body after 4 hours. Well, that's going to be fairly simple, because up here we have the amount of caffeine in the body after 5 hours. So if I want to make it 4 hours, all I'm going to do is simply replace the 5/6. I'm going to make that a 4/6. And of course, we know that 4/6 is equal to 2/3. But the key is I replace the 5/6 with 4/6. Okay. And then reduced that fraction 4/6 to 2/3. So that is my answer to number 7. Okay, number 8. Write an expression to represent the amount of caffeine left in the body after H hours. Okay. Well, all I'm going to do is, once again, is I'm going to take this, just like I replaced the 5, 6 with 4, 6. I'm going to make the 4 an H. Okay. So now, if I want to know the amount of caffeine left in the body after any number of hours, all I need to do is take the number of hours and divide it by 6, and that tells me the number of 6-hour time periods. Okay, so that is the answer to number 8. Number 9, using your expression, what appears to be the decay factor per hour? Now, to find the decay factor per hour, my decay factor per 6 hours is a half, okay? Because it's decreasing by 50% every 6 hours. So my decay factor per 6 hours is a half. To find the decay factor per hour, I'm going to play the same game that I did up here when I did this question. So I'm going to take this expression here, and I'm going to do some creative algebra. So I'm going to make this I'm going to make this 0.5 to the power of 1/6 to the power of h. Okay? Just like I did before, these two expressions are equal because if I multiply 1/6 times h, I get h over 6. Okay? And by separating that out, I now automatically know my decay factor per hour. My decay factor per hour is equal to 0.5 to the power of 1/6. So it's not 0.5, it's 0.5 to the power of 1/6. And that is my answer. That is my answer to number 9. A 0.5 to the power of 1/6.